where I can see you. Okay. So I believe this is where we left off when the sirens went off, which fortunately ended up being a false alarm. But I think we ended with the video camera. Okay, and we talked just a little bit about this yesterday. So what you see in this diagram here is the image intensifier. And then this little device here, that represents either lenses or it could be fiber optics. And that is what will send the light photons from the output phosphor to the video camera. Because the video camera, what it needs to do is it needs to take those light photons and it needs to convert those photons into electrons, because we have to have electrons sent to the TV monitor in order for the image to be displayed. So the whole purpose of the video camera is just simply to take light photons and convert them to electrons. And there are different types of TV cameras. And we had mentioned one that's called the Vidicon. And the Vidicon is a vacuum tube, and it really would exist in older equipment. I seriously doubt that you would be dealing, well, you wouldn't be dealing nowadays with a unit that has a Vidicon unless there is some old office somewhere in the middle of nowhere where they just haven't upgraded their systems and they're still using film. Because when you use that Vidicon, the only way to get a permanent image is to use film to capture those images permanently. And it's something like, 99.9% of facilities now have digital imaging. So anyway, even our unit down in the lab, our TV camera isn't a Vidicon, it's a CCD. It is a CCD. All right, so if the unit has a CCD video camera, like ours does in the lab, the video signal or the electrons, because remember, it converts it to electrons, the CCD does. So what happens to those electrons is they can be sent to an analog to digital converter. And that analog to digital converter, it is located between the video camera and the display monitor. In other words, it's hooked up to a computer. And so those images can be permanently stored. So not only can we create those digital images and store them on the computer, the images are also sent to the monitor so that you can see what those images are during the fluoro study. So when individuals talk about digital fluoroscopy, technically it includes our type of unit that we have down in the lab. Our image intensifier unit, since it has a CCD built into it, it is technically a type of digital fluoro system. Okay. So you okay with that? So if you had to identify two video cameras, you should be able to recognize Vidicon and CCD as video cameras. Which one will allow for digital images? The CCD will. Okay. All right. So we did the image intensifier, and then we also did the video camera. There are just a few things that you need to know about the image intensifier, some issues that exist, and these are the names: pincushion, vignetting, and veiling glare. Okay. Basically, what pincushion distortion is when you look at the monitor. Okay, when you look at the monitor, because an image intensifier was used, what happens is we get stretching of the structures around the periphery, and it's because the monitors that the images are displayed on are, and I should have pointed this out to you yesterday, but they're cathode ray tubes. They're really deep. You all have seen this, though, whether you've been in fluoro or not. You've probably seen it in the imaging suite. and even computer monitors. You know, the old computer monitors that were really, really deep. They're not flat panel monitors like we have now. No, they're those big, bulky. Well, when you look at those monitors, the screen, the glass is rounded a little bit. Okay, it's rounded a little bit. And because those screens are rounded, when the image displays, it actually kind of stretches the periphery of the structures. And the reason that can be an issue is because it can take away from the spatial resolution from the structures along the periphery of those structures. So you need to be able to recognize the name pincushion distortion, and it means that the structures on the edges will be a little blurry because it stretches out those structures along the periphery. And it's because the screen that we view it on is rounded. Okay, so it just stretches out the structures. Instead of them being flat, it's stretched out. And then another term is called vignetting. And because of the display that the image is displayed on, there is decreased brightness of that image along the periphery. So along the edges, there's also a decrease in the image brightness. And that's just something that happens that we can't control. So that's what vignetting is. It's just simply decreased brightness. Okay. And then the last thing that occurs when we use an image intensified system because of the monitor that we use to display the image, we actually end up with a decrease in image contrast, a decrease in image contrast. And it's actually because of the light coming from the output phosphor. It increases electronic noise in the system, and then it displays the control panel can't correct for it, and so it just displays with decreased contrast. You don't need to know exactly why and what's taking place. What you need to know, what's important for you all to be aware of, is that anytime an image intensifier is used and that image is displayed, it's actually going to have lower contrast than what the object actually has inside of the patient's body. And it's just because there's a certain amount of inherent noise in the system. So veiling glare just means that there's a loss of contrast. That's all it is. So would you be able to pick those three out and match them to a definition? Think so? Okay. All right. So that finishes up the information for image intensifiers. Okay? That's all image intensifiers. Now, the newer systems that are in some facilities may look like this. Have any of you seen a system like this in fluoro? Where were you? Over at Duke?
One of the UNC rooms has this.
That's right, the newer UNC room. And then Gabby, were you at Duke? Have you seen a unit like this at Duke? Somebody was shaking their head yes. I don't know if somebody saw one at Duke.
I think Gabby went to UNC Fluoro as well.
Okay, because at Duke they have a unit that looks very similar to this. And this is a flat panel detector system. You may hear, and this is a digital system, but for some reason, some individuals will only refer to this as digital fluoroscopy, and the image intensifier, they won't refer to that as digital. But the image intensifier system does have digital capabilities as long as a CCD is connected to it. Just like I told you in our lab yesterday, since our image intensifier system has a CCD, those images can be stored on a computer. We have digital images. But this newer technology, it's a flat panel detector. So flat panel detectors can serve not only as detectors for general diagnostic radiography, flat panel detectors can also be constructed and used for fluoro systems. They're just a little bit different in terms of how fast they read the charges out, because fluoro is real-time imaging. So as soon as the information is picked up by the detector, it's releasing it immediately. So it's the timing is just a little bit different. Okay, but still the composition is the same, with the flat panel detectors. So what the flat panel detector does is ultimately the X-rays do get converted into electrons. So, the amorphous selenium, because they tend to be the direct conversion flat panel detectors. So the X-rays come in, interact with amorphous selenium, and we end up with electrons. And, that's our image data. So the nice thing about this flat panel system is that big bulky image intensifier is gone. And then also the video camera, there's no need for the video camera. And there's also not a need then, of course, too, for the coupling system, the lenses or fiber optics that couple the image intensifier to the video camera. So in essence, you're getting rid of three components: image intensifier, the lenses or fiber optics, and then the video camera. So the device, when you look at it, it's a lot more streamlined. This type of unit, because it is a flat panel, and even though it's a little bit different in terms of its response time, it can still be used for general diagnostic imaging. At the push of a button, you can convert its use from fluoro to general diagnostic radiography. Down in our lab with the image intensified unit, if I want to do just regular X-rays, then I need to move that big fluoro tower out of the way and bring my X-ray tube over. Then if I want to convert to fluoro, I need to move my X-ray tube out of the way and bring that big heavy fluoro tower over the table. With this, the X-ray tube is already in place here. So at the push of a button, it just converts from radiography to fluoro. You don't have to move anything out of the way. So it just makes it a little nicer. Notice though, the X-ray tube is over the table. The flat panel detector is located down here below the table. There tends to be less radiation exposure to the patient because the flat panel detector does directly capture those X-rays, so we don't have as much data loss, and that's why the technique can actually be, or the exposure can be a little less to the patient. With the image intensifier, because there's so many layers it has to go through, inevitably you're going to lose some of that information, and so the exposure factors have to increase to compensate for that. Okay. It does also have magnification mode, but unlike image intensifiers, the dose to the patient may not increase. It may not go up. She's waving to everybody. So we won't go into detail with the magnification mode because when it comes to this type of system, there are too many variations with the vendors, but just simply know that there are magnification modes, but that the patient exposure may not actually increase in mag mode like it does with the image intensifier. Okay? You okay with that? So that was the flat panel system. See how long it took us to do the image intensifier, and then the flat panel detector system, it's like that. Okay? All right. And you will find on that flat panel detector system the same type of buttons in terms of, there will be a button for mag mode, there will be collimator buttons, that type of thing. So you're going to have those similarities there. All righty. So now I'm going to talk about automatic brightness control. And this is something that exists on the image intensifier units as well as those flat panel units. So ABC, we talked about it a little bit yesterday. It's also known as automatic exposure rate control. You do need to recognize AERC because that is the newer term that's being used. Okay? So we talked about it, and what it does is it will just it'll alter the exposure based upon the structure that the radiologist is over. Normally, when we start out, the KVP could be anywhere in the 70s to 120, somewhere in that neighborhood. But that KVP, it will vary potentially as that fluoro unit is moved. So we said yesterday that the unit could either adjust the KVP or the MA, or it could adjust both factors. It just depends upon how the vendor has set that equipment up. But it just adjusts the technique for the different tissue types. Okay. Do you happen to remember what I told you yesterday, that it's not in the textbooks, but some vendors, instead of adjusting MA or KVP, that there's something else that they will use to adjust the exposure?
Filtration.
Yeah, filtration. They can have a filter automatically moved in and out of the beam to adjust the exposure rate. But all you need to know are MA and KVP. All right, so that's the ABC or AERC. Are you okay up to this point? Okay. Now, modes of operation. Do the best I can here to walk you through this. Remember, every type of X-ray unit has a power supply, and we talked about generators. That's the power supply for the equipment. And we talked about single-phase generators, three-phase generators, high frequency generators. So in other words, that is just the power supply. Okay. Now, with older fluoro units, the generator would, when that power supply would come in, it would operate on continuous mode. And what that means is whenever the radiologist had their foot on the foot pedal, or they were pulling the finger switch for the fluoro, the X-ray beam was continuously on. Okay, so, if they've got the foot pedal down, they have their finger on the trigger, there's a continuous flow of power through the system, resulting in a continuous flow of X-ray tube output. Because that was called continuous mode. And that was typical through the 1980s, okay, through the 1980s, and even a little bit beyond that. Okay. So the generator will produce a continuous beam of radiation. Now, in terms of the MA, the milliamperage that would be coming or used for that, it would be around 3 to 5 MA. Okay, 3 to 5 MA. And the reason the milliamperage is so low is because, with fluoro, if the X-ray tube is constantly on, we want to avoid overheating that tube. And so it operates at a low MA. Okay, it operates at a low MA, 3 to 5 MA. So our unit in the lab, it operates at around 3 to 5 MA. So if we press the exposure switch for fluoro, it's got about 3 to 5 milliamps running through the circuitry. Okay, so very low amperage, because we don't want to overload the tube and cause damage to the anode. Okay. Now, the Vidicon or the CCD, which is typically the case now, remember, it sends the image that it received from the image intensifier. It sends it to a TV display monitor. So the CCD will send the electrons to the TV display monitor in order to be displayed so we can visualize it. The way in which it does it, though, is important. Okay, you see this thing here that's referred to as interlaced scanning format. And we'll look at this in a second. It's on the next slide. And so hopefully what's on these next two slides, it'll come together for you. So the rate at which these electrons are sent to the TV monitor is at a rate of 30 frames per second. We'll get to this, okay? 30 frames per second is necessary to prevent the image from flickering on the monitor. When the image is displayed, if it flickers, that would be very annoying for the radiologist to look at that image if it's flickering. Okay. You know, when you look at your TV or you look at your computer, the image isn't flickering. It would be annoying if the image would flicker. Okay. Now, it takes about 33 milliseconds for a frame to be scanned, and you know, we'll get to this. Okay. 33 milliseconds for a frame of an image, which, by the way, 33 milliseconds. Well, I'll get to that in a second. 33 milliseconds is a long time for a frame. Okay, for a single image. During those 33 milliseconds, a patient could end up moving. Okay, could end up with some motion blur, and that's, you know, one of the downsides to having a fluoro unit operate in this continuous mode, because there's a lot of time for the patient to move, and then the image would display with a certain amount of blurriness. Now, what do you know about MA in time to yield a particular mass? So I'm going to divert for a second. When we talked about mass, did we talk about the fact that you can use different MAs and different times to yield a certain mass? We did, right? Okay. Generally speaking, do we want the highest MA and the lowest time, or do we want the opposite? So in other words, do we want high MA in short time or low MA in long time for a particular mass?
High MA in short time.
High MA and short time, right? That's what's ideal, okay? So let's go back to this for a second. 3 MA and 5 MA, that is extremely low milliamperage. Because remember, when we talked about MA stations on our diagnostic equipment, you know, we said there could be 100 MA stations, 200, 300, 400, 500, all the way up to like 1,000 MA or even 1,200 MA. But, you know, with fluoro, we are using an extremely low milliamperage because we want to avoid overheating the tube. Okay. And the reason then, if you look, I said our exposure time's at least, you know, it's like 33 milliseconds. The exposure time for fluoro has to be long in order to use a low MA. So if we're using a low MA, the exposure time has to be long to get the appropriate mass. And the reason our exposure time ends up being long is because it's tied to how that image displays. And we have to have a long enough period of time for our image to display, or our image would flicker. So all of that is tied together. So the units will use a very low MA and a long exposure time. So the downside is, you know, the patient could end up moving. But the reason we have to have a long exposure time is it's for a couple of reasons. We need to use a low MA to not overheat the tube, and we need a longer time in order to give the unit a chance to display the image. Okay, does that kind of make sense? So our image intensified unit in lab uses a very low MA and a long exposure time. And it has to use a long exposure time because we have to give the unit a chance to also display that image. Okay? And it has to do with this interlaced scanning format here. So this is what you're seeing here. Interlaced scanning means that the image is created in 2 parts. Okay. So when the electrons leave the CCD and they're sent to the TV monitor, this is how the image is displayed. This is how it displays those electrons and converts it into the image. It displays it one line at a time but it's every other line. So it will display the image from left to right and top to bottom, but notice that it skips a line. So it's tracing this image on that display panel from top to bottom, and it's left to right, but it's skipping a line. Okay. This is what is referred to as a field. That's one field. Then what it does is there's a mechanism in there. It's something called an electron gun. We're not going to go into how that thing works. But then this electron gun fires those electrons that it receives from the CCD, and it goes back to the top of the screen, and in a left to right pattern and top to bottom, it fills in the other lines. And so when those lines are put together, you end up with that entire image. Okay. It takes approximately a 60th of a second to do this field and a 60th of a second to do this field, which gives us 30 frames per second. And all in all, it takes about 33 milliseconds to do that. Okay. So when you look at the monitor, this is happening rather quickly though in terms of how it is displaying it. That we don't see this. We don't see this happening. All we end up seeing is that final product, that final image. Okay. But because the system has to do this interlaced pattern in order to display the image, that's why the exposure time has to be 33 milliseconds. Because we have to give the TV monitor time to display the image before another image is sent to it. And that's why the exposure time is long. Okay? That's why the exposure time is long. This is ultimately what we end up seeing. And this is referred to as a frame. And the system will actually end up displaying 30 frames per second. So we get 30 of these per second, believe it or not. And that just simply means we do not see the image flicker when it comes up. Okay? So I kind of wanted to give you an idea as to how this works. In terms of important takeaway points, what you need to know is that if a fluoro unit operates on what's called continuous mode, it means that X-rays are continuously coming out of that unit. And if it's that type of fluoro unit, it has to operate on a low MA, 3 to 5 MA. Okay? So if it's continuous like the one we have in lab, the MA is really low, 3 to 5 MA. Okay? The other thing that you need to know is if it's a unit that operates on a very low MA, the way the image will scan to the TV is in an interlaced scanning pattern. Okay. Interlaced scanning pattern. So this is how the image is being created, and then that is what we actually see. But it's called an interlaced pattern. Okay. Can you at least handle that much of it? So if you have a unit that has a very low MA, what does that mean in terms of the X-rays coming out? Is it continuous?
Mm-hmm. Yes.
Okay, it's continuous. The image displays as a full image because of this interlaced pattern. Okay, this interlaced pattern. Now, newer units are different. Okay, newer units are different. So those of you that have worked with a newer fluoro unit may have either seen on the control panel or heard the technologist about setting a pulsed mode. Did anybody hear about that? You did? You got to see that, Brianna, or heard about it? On the control panel, you may see some buttons like this: 30, 15, 7.5, 3.75. Did you happen to see something like that?
I just saw a pulse. That's all I saw.
I'm sorry, what?
I just saw like they would press pulse at some point and then they would turn it
Okay.
off.
Okay. And they could have it default to a particular pulse, but you did see them push pulse. Okay. Newer X-ray units, the way the incoming power supply will work to that unit is the X-ray beam will be pulsed. So this is what it looks like. So this represents tube output, and this is just time. So what the X-ray machine does is it will send out a burst of X-rays, then there'll be a little gap of time, send out a burst of X-rays, then a little gap of time. So even if the radiologist has his or her foot on the pedal or they're pulling the finger switch, the X-rays don't come out continuously. The X-rays come out, and then there's a brief break in time. Then they come out again. Then there's a brief break in time. So even though that foot pedal's being held down constantly, or the finger is on the switch for fluoro constantly, there is a break in the X-ray beam. Okay, there's a brief downtime where that X-ray beam turns off. Okay, now because the unit operates like this, those units can use a higher MA. And so if the unit can use a higher MA, what does that tell you about the exposure time that is needed to generate the proper amount of mass for the image?
It'll be shorter.
It's going to be shorter. So there's less chance for patient motion with these types of units. Okay, with these types of units. All right. So again, the CCD will send the electrons to a display monitor, okay, to a display monitor. And the way the monitor will display the image is different than the older units, okay? It's referred to as a progressive scanning format, What that means is it is left to right, top to bottom, but it doesn't skip a line. And so this happens very rapidly because the TV monitor is not having to go back up and then fill in or scan in the gaps of the image, in between. So this happens very quickly. So since the image display is able to happen very fast, that's why we're also able to use a high MA and a very short exposure time, because the image will display very quickly and then it can move on and display the next image. So everything can happen very rapidly because of the time factor in this whole chain of events. So the exposure time is really short when you use a pulsed unit. You don't need to memorize this, but I just wanted to show you in comparison to the 33 milliseconds. We're talking about only 10 milliseconds to 3 milliseconds to get an image displayed, for image display to occur. So we do end up with less chance for image blurring. And the thing with these pulsed units is there are oftentimes buttons to select different pulse rates. So you can further reduce the exposure to the patient. If you operate a unit at 30 pulses per second, then that is going to be the highest exposure to the patient. 3.75 will be pulses per second is going to yield 3.75 frames per second. So in other words, what happens is the exposure is reduced. The exposure is reduced. So what you need to understand about this particular type of unit is that with a pulsed unit, even though the operator of that unit has the exposure button on continuously, we don't get continuous x-rays coming out of the tube. We have little breaks in that exposure time, which means that gives the patient a break in terms of exposure because there's some downtime. And the reason we can have this happen is because the images display so quickly. We don't need that x-ray beam continuously on in order to create an image. We're able to have a little bit of downtime. And so that's what's called the pulsed mode, and the images are displayed in a progressive scanning format. So that's what you need to know. Newer units have pulsed mode. It displays the images in a progressive scanning format, so that allows exposure time to be low. Okay. And know that if you see numbers like this, that the lower the number, that means there's more dead time during the procedure, during the exposure. So patient exposure is reduced. And just as a comparison, just as an idea, if a unit allows you to switch from 30 to 15 frames per second or pulses per second, patient exposure is reduced by about 35% from 30 to 15. It's about a 35% reduction. That can vary a little bit from unit to unit, but that's just an approximation. So that is a significant reduction in exposure just within a pulsed unit, in and of itself. So lower pulse, what happens is as that pulse gets lowered, like if you move down to 7 pulses or 3.7, you're reducing the time for motion to occur, and your images can be sharper, and you can even have less exposure. Okay. The reason, though, you might not always use these lower pulse rates is because if you're imaging things like cardiac studies where you need to see the heart beating, that heart movement, you may need that higher pulse setting because the heart beats very quickly, and you would have too much downtime if you used a slower pulse rate, and you would miss some of that heartbeat. That's something if you all were to go into cardiac cath. So when you do your fluoro rotations, pay attention to the control unit and see if you notice these numbers and what is being selected for the particular study you're doing. For pediatrics, you might see that they're using lower frame rates here to reduce patient exposure. Okay. All right. You think you can keep that information separated?
I have kind of like a sidebar question about the pulse. So when I was in the OR last week, the doctor wanted the subtraction feature, but it wouldn't work if the pulse button was selected. Is there a reason for that, or is that just like a issue with the machine or something?
Yeah, it typically, and now I'm not going to say 100%, just in case there's something out there, because sometimes there could be something a little different out there. Typically, yes, you have to take it off the pulse mode in order for the digital subtraction function to work. So you have to get it out of that mode, and then activate the digital subtraction function so that it can essentially reverse what that image looks like. Did they finally get it to work?
Yeah. After a while, they called someone in, and then the guy was just like, "You have to take the pulse off," and they were like, "Oh." So yeah.
Typically you do, but like I said, I don't want to say 100% just in case there's something new out there, but typically, yes, you have to disengage it from that pulsed function in order to use a different function. Yep. Okay, so if you're asked about fluoro and it has continuous x-ray output, remember the MA has to be low. Okay. and the image scans in an interlaced pattern. If you have a pulsed fluoro unit, you can select different frame rates, and doing so will change the amount of exposure the patient gets. Okay? And the way the image displays is called the progressive scanning, where it does display a line at a time. Of course, you can't see that. All we see is the final image because it does happen so rapidly. Okay. All right. And then let's just do image display, and then we'll take a little break. Image display, those video signals, those electrons, like we said, do get sent from the CCD to a monitor. You'll see different types of monitors out there, and we kind of already mentioned this, but this is a cathode ray monitor. It's really deep. It's bulky. Okay, these cathode ray monitors are the ones that are used like with the older fluoro units that use the continuous fluoroscopy. Okay, and it's because the images have to display in an interlaced format, and it's because of the technology that is in that cathode ray tube. It can only display the image a particular way, and it can only do it so fast. Okay. With these cathode ray monitors, they're low resolution monitors. If we end up with approximately what's called 525 lines per frame, that yields a low resolution image. In fact, if you go back a few slides, you see where I have here where this field was produced with 262 and a half lines, and this field was produced 262 and a half lines. When you add those two numbers together, you get 525 lines. So these display monitors have very low resolution. Okay. Monitors such as liquid crystal displays or plasma monitors, which are these type of monitors here, yield higher resolution, anywhere from 1,023 lines to 2,048 lines. So we've got better spatial resolution with these monitors. So in essence, it's like having smaller pixels. Okay, the pixels are smaller, so we have a higher resolution. And we're able to have higher resolution with these monitors because of the type of technology that is built into it in terms of like the pixel size. And with these types of monitors, the way that image is created is by that progressive scanning format that we talked about, where the electrons are displayed a line at a time from top to bottom, left to right, and ultimately we do end up with higher resolution with this type of technology. Okay, so this is what we have in the lab. This is what some of you will be seeing in clinic with the newer units. So if you see this, you know that unit is going to be a pulsed unit because of the way it can handle displaying the image. All right. All righty. I tell you, let's just hit image recording and storage, and then we'll take a break, because then essentially all we have to go over are Code of Federal Regulation type of stuff. For image recording and storage nowadays, it is digital based. We have computer hardware attached to the system. We do down in the lab because we have that CCD chip built into our system, so we can store the images on computer. With the flat panel detectors, those newer fluoro systems, the same thing. They are digital systems. Computers will store information. There is software built into the system that will allow for post-processing of those images. Images can be sent as static images. You can take single images, or they can be recorded as video. And you may hear that referred to as cine. Okay. So those fluoro units, whether it's the new unit or even the unit like we have, we can take single images, or it can be recorded as a video. Okay. And so basically that's it for the storage. All right. So do you all want to take 10 minutes? Or how about how about 11 o'clock? We'll just make it even 11 o'clock. And then we'll just look at these recommendations and regulations. Okay, so I'll see you at 11.